is Shane Picard with another geometry lesson. Today we're talking about the areas of trapezoids, rhombuses, and kites. And we'll start with the area of a trapezoid. How do we calculate the area of a trapezoid? The formula is pretty straightforward. The area of a trapezoid is equal to half the product of the height and the sum of the bases. As an algebraic equation, it looks more like this. Area equals 1/2 h times the sum of b1 and b2. The bases are always the parallel sides of the trapezoid. It does not matter which one is longer or shorter. It just matters that we take them both into account when we add them together here. The height is the perpendicular distance between the bases. I've indicated it here, but it could be anywhere along here as long as we're talking about the perpendicular distance between those bases. Let's take a look at how we derive that formula. I have here a trapezoid. We'll make an exact copy of it, and as we make the copy, we'll rotate it 180 degrees. Now you can see I've got two trapezoids. They are congruent. One is simply upside down. If we take the trapezoid on the right and slide it to the left so that it meets the other trapezoid, you can see we now have a single figure, which is actually a parallelogram. Remember, these bases are parallel, and so we find that this is actually a parallelogram. We know the area of that parallelogram is base times height. This is the base of the parallelogram, and this is the height of the parallelogram. We also know, because of the way that we constructed this parallelogram, that the base of the parallelogram is equal to the sum of the bases of the trapezoid. In other words, if this is base 1, and this is base 2, and up here base 1 and base 2, the sides of the parallelogram, or the bases as we call them in this context, is actually equal to the sum of those two numbers because it's this entire length here. The height of the parallelogram is identical to the height of either trapezoid. So we know the parallelogram has area equal to base times height. That's the formula. We also know that this corresponding parallelogram has exactly twice the area as each of these trapezoids, since we took two trapezoids to create the parallelogram. Therefore, we can be sure that the area of one of the trapezoids is equal to 1/2 the product of the height times the sum of the bases. And that's how we derive the formula. Area is equal to 1/2 h times the sum of the bases. Let's look at one quick example. Suppose we have this trapezoid. It has bases 8 and 12 units and height 6 units. Find its area. We know area is equal to 1/2 height times the sum of the bases. So we know that area is equal to 1/2 times 6 times 8 plus 12. Therefore, area is equal to 3 times 20. Area is equal to 60 square units. 60 square units. Notice one more thing about the formula here that may be helpful for some people. If we rearrange this, we can express it as area is equal to h times 1/2 base 1 plus base 2. Commutative property of multiplication allows us to move those factors around. You'll notice if you look at the right portion of this expression, there's actually an indication of average here. We're adding two values together and then dividing them. And in fact, we find if we were to go ahead and find that segment length, that is half of b1 plus b2, it would actually be right across the middle here. All we're doing is multiplying the average width of the trapezoid by the height of the trapezoid, and we find that that is the area. Now let's talk about the areas of rhombuses and kites. Formula for the area of a rhombus is the same as that of a kite. So we need to just derive one of these, and then we should be good to go. Remember, as we do this, that rhombuses and kites have perpendicular diagonals. Because that property exists in all rhombuses and kites, it allows us to create a formula very easily. Here is a kite. For our purposes, it could just as well be a rhombus, but we're starting with a kite. Notice it has two pairs of congruent sides here, and that those sides which are congruent are also adjacent. First thing we'll do is draw in the diagonals, and note again that the diagonals are perpendicular. After we've put the diagonals in, we're going to draw lines parallel to the diagonals and basically enclose the kite in a rectangle. Looks like this. So there's a lot going on here, but what do we have? We have lines here that are parallel to the long diagonal, and we have lines here and here that are parallel to the short diagonal. Notice that we have a rectangle which is surrounding this kite, and I've also added in letters so we can talk about each of these different points. So we have rectangle HEFG, which is surrounding kite ABCD. Now the next thing I'd like to do is just focus on one of these four quadrants. You'll notice that the way that we've set this up, we basically have four quadrants. 1, 2, 3, 4. I'd just like to focus on one of those for a moment, and we'll look at this one here, which is also a rectangle BFCI. Note that inside rectangle BFCI is diagonal BC. And we also know that the diagonal of a rectangle divides the rectangle into two congruent triangles. We could prove that pretty easily because the rectangle is a parallelogram and BC, segment BC, is a transversal. We know by the alternate interior angles theorem that these two angles are congruent, and we also know that these two angles are congruent. So by angle side angle, we have two congruent triangles. That means that the area of triangle BCI is exactly the same as that of triangle CFB. They have exactly the same areas, which means triangle BCI has exactly half the area of rectangle BFCI. In other words, if we can calculate the area of this rectangle, we could divide by 2 in order to know the area of this triangle. Now let's go back to the big picture again. We have 4 rectangles. Each one is divided in half by a diagonal. Our kite occupies one triangle in each rectangle. Therefore, we can conclude that our kite occupies exactly half the area of this rectangle. So if we could find the area of that rectangle, we could very easily find the area of the kite by just dividing it into 2. Well, how do we find the area of that rectangle? It turns out that all of these lines are all the same length. In other words, BD is the same length as HE. Also, these 3 lines in this direction are parallel and all the same length. So if we wanted to know the area of the rectangle, we just multiply the base times the height. And of course, that would give us the area. Therefore, if we simply multiply the diagonals of the kite, we'll also know the area. And that leads us to the formula for the area of a rhombus and kite. The area of a rhombus or a kite is half the product of the lengths of its diagonals. Here in symbolic form, we have A equals 1/2 D1 D2. Let's look at a quick application of that and see if we can make sense out of it. Here we have a kite, and you can see that the segment here in the top of the kite, if you want to call it that, is 2, and we have a segment that is 6 down here, and then we have 2 segments here, 3 and 3. So how do we find the kite's area? Area is equal to 1/2 times the product of the diagonals, and so therefore area is equal to 1/2 times 6 times 8. This is 6, and this is 8. And so we find that area is equal to 24 square units. And that's how we find the area. Exactly the same process in a rhombus. Same exact formula. A equals 1/2 D1 D2. Make sure you work through a few problems on your own. And as always, if you have any questions, send me an email.